Okay, so this formula for independent sets gives us the formula that I stated earlier about maximum clique size. So what's the maximum clique size? If you think about it, so we have a similar formula for maximum clique size. Now suppose that you want to calculate maximum clique size of a graph, okay? What's the maximum clique size? It's the complete subgraph where any two vertices are connected to each other. Now consider the complement graph. Inside the complement graph, a complete subgraph will be an independent set. Because remember, complement graphs were exact graphs where if you have an edge here, you don't have an edge here. If you have no edge between any two vertices, it becomes an edge here. So independence number of a complement graph will be exactly the maximum clique size of the original graph. Right? So suppose you want to find the maximum clique size of here, which is 3. If you look at the complement graph, a clique size of 3 gives you an independent set of size 3. So the relation between graph and graph complement with respect to these things is that maximum clique size of G is same as independence number of the complement graph. In the same way, maximum clique size of the complement or independence number of G is same as the maximum clique size of the complement graph. So sometimes you can use this to pass from one to other one, which means this inequality also can be used to estimate something with MC, right? So the estimation was you get this 1 plus degree, but now this degree is the degree of the complement graph, degree in the complement graph, right? So it's the GC. But what's the relation between degree of the original graph for a vertex I and degree of its complement graph? So suppose in G it has degree D is equal to D, say D sub D sub, say A. What will be in the complement graph, degree of the same vertex? So all the places that we weren't going before, we weren't connected, now we are connected, and the places that we were previously connected by edge, we are not connected anymore. So there's a complement relation, right? So in the complement graph, if degree is A, in the normal graph, if degree is B, say like this, what is the relation between A and B? Just got it. So if you have a vertex, its degree in the G is A, its degree in the complement graph is B. What do you can say about A and B?
A plus is equal to
N minus 1, yes. So their total should be all possible places you can go, but because you cannot go to yourself, you have N minus 1 places to go. Which gives us very nice formula for the degree of the complement in terms of degree of the original graph. Their sum is N minus 1. Okay? So I can use that here just to change this. So if their sum is N minus 1, I should say that this degree is this. But you can immediately see the 1 cancels, so you get n minus di. So the conclusion is this formula that maximum clique size of G is bigger or equal to the sum of the vertices with 1 over n minus di, where d now referring to the degree of the graph on the graph G. So original graph now. Oops, sorry, this is original. Here the formula was 1 plus di. Here the formula is 1 over n minus di. So it's very similar, but slightly different. I already gave one example last time I introduced this. I think the example was something like this: 1, 2, 4, 5, 7, 6, 3, and this. Something like this. Okay, you can see that degrees are these. By the way, I made one mistake in the previous degree calculation. One of the, let me show you this. This was not 3 but 4. You can check it in your notes and make sure that it's correct. So it changes a little bit. So this number is slightly different. Okay. Just go through it and you can verify it your own calculation. So make sure that we don't make mistake here either. So here maximum clique size should be bigger than sum over 1 over n minus di. So you use these numbers to estimate the maximum clique size, and because the total number of vertices is 7, these numbers that you're adding is the difference between 7 and these numbers. So there you have these. And I think I did last time this calculation, maybe hopefully correctly. This is 7 over 4, and then 15 to 5, 75, 60 plus 22 over 60, 97 over 60. So it's, last time I had a better number. Maybe I did some other graph. Yeah, I had another example last time, I think. And for this example, is your estimate is this, and then this is about 1 point something, 1.5. As you see, there is much bigger, like clique sizes of 3 exist here. Been knocked out. I mean, yeah. So the estimation you get is 2, bigger than 2, but you already have 3 triangles here. So it's again, it doesn't give you the maximum clique size. It gives you a lower bound for it, and this lower bound can be much smaller than you want. Last time I had an example which was the exact number. This is an example where it's much smaller. So there's no requirement that it gives you the maximum clique size. But in many cases, like you're trying to find a clique of size 10, and then maybe maximum clique size is 20, but you don't care. You just want to verify if you can find one with 10. So if this number is 10, then you know that maximum clique size is bigger than 10. So that will guarantee you that you can find a clique of size 10. Okay. I don't know how necessary to make this more real life, but like you're looking at Bilkent students' Facebook data, for example. You can say, among the Bilkent students, I can always find 20 students who are friends with each other on Facebook in pairwise. That will be the clique size of Facebook graph of Bilkent students. I mean, 20 maybe is too big number, I don't know. If you have to make a guess about how big the set size you can find so that any two students are friends on the Facebook, do you have a guess? What will be the clique size of Bilkent student Facebook friendship graph? 20 is too big? You will say, huh? Even more? You can find? Maybe. Like in the dormitory, everyone on one corridor probably friends on the Facebook. So you may get 30 people. But it has to be, any two has to be friends. You think it's bigger than 20? 30? 30 maybe? Yeah. Much bigger. 50. You can find 50 people who are pairwise friends on Facebook. You're more connected than I expected. I guess 50. But now this says that every student has a Facebook friendship number, right? It's about 50. How many friends you have on Facebook, for example? 800? 300? And we have 2,000 students, or 8,000 students. So we have 8,000 students. 300 is a good number, or is it too low? Like, what's your friendship number in Facebook?
500.
500. So your degree is 500 on the Facebook graph, right? So these degrees are these numbers. So let's say average you have 400. So you'll be looking at 800 minus 400, 1 over, summed over 800, 8,000 people. So what's that number? So it's 8,000 divided by 8. I guess 1 minus 400. No, it doesn't work like that, does it? So what is this number? 8,000 or 7,600? So 1 divided 4 or 76. So what's the estimate for 4 over 76? It's 0.5. It's 0.05. It's about 5% of 80, right? 5%. So that means it only tells you that you have a clique of size 2. It's a bad. What did we do wrong? So with 8,000 students, that means you have to have more than 400 friends in Bilkent. This is also the fact that your friends are probably outside of Bilkent. So inside Bilkent, 400 is not even a good estimate, right? So inside Bilkent, maybe this is much smaller.
It's smaller, it gets worse.
It gets worse even, yeah. So if you have 8,000 students, to have a for big graphs, this is terribly bad estimation, right? For big graphs, to say that you have a clique of size 50, that's why I was surprised. I mean, in 8,000 students, to have a clique of size 50, to guarantee such a thing, you have to have about like 5,000 friends, each of you, in Bilkent. I mean, otherwise, how do you guarantee? Because this complete graphs are very hard, right? Every pair has to be connected. I mean, complete graphs. I actually don't think that 50 will be click size here. I mean, 50 is too big. You have 50 people, you know that they're all friends with each other.
I think this graph representation is not very useful for this conversation.
This estimation.
Because it's more probable that I am a friend of my friend's friend rather than somebody who is very away from me.
Yeah, so the graph is a little bit like
Yes,
distorted. Like there's this big things, but yeah, there's this maybe not much connection between these, but once it becomes very dense. Yeah, I see. There are people probably studies these kind of properties of graphs, that intensity of, if you know someone and like the Newton, they know each other is much higher than, yeah, in Facebook, for example, they already send you all these invitations of, if you are friends with someone, their friends are already reminded to you that you should make them friends too. So that increases actually click sizes. Yeah. Okay, this is a rough estimate, but as you see, it is an estimate, and you can use it to get some results. I read somewhere that the reason these companies like Google and Facebook are so worth quite a bit, although there's not much advertisement going on at this point, is the data, the graph data that they have is very valuable. That tells you quite a bit about how things are connected in the society.
I read a report paper about how obesity spreads
among the Facebook graph. Yeah, I mean, many researchers will want to buy this data, and then each time they have to negotiate probably with Facebook. I also read that Google data, what you search, also when you put your use Google Archives, like the memories, if you put your pictures and documents in Google, they're being used there for general search engines. Like you can do artificial intelligence machines using this data. So in the future, the data will be so valuable that companies becomes valuable because of that. But that's. But anyway, the Facebook graph is something that if you search on Google, many things comes up. So it's not just many people are interested with these things. Okay, two things that to get from this. One is immediate result you can get using this. Is this if G has n vertices and A edges, then there's this crude estimate, even more cruder than this, something like this. The way this obtained is from this, but you have to also, so this is, the proof is not going to give you complete proof, but the two things that comes into it. First of all, you know the sum of degrees. We know the sum of degrees is twice the number of edges. So when you have A, we know that this is 2A. Okay? So that restricts the numbers that you're putting in this thing. So when you look at this estimation that is given by this, now you're looking for numbers that you put here, but their sum is 2A. So you have discrete data, d1 to dn, which sum is 2A, and you're summing 1 over n minus di's. So this turned out to be bigger than possible minimum of all such sums where the xi's have the property that their sum is 2a. So you can try to estimate what is the smallest number you can get by summing 1 over n minus xi's, so that the sum of xi's are this. And again, this is something to do with n over 1 over n minus x graph. What's the minimum number of points you can take whose sum is 2a on this graph? And this graph is just calculus. For every x, you get 1 over n minus x. So, I mean n minus x, but this is like minus 1 over x minus n. So n is the fixed number. So you can see that something like this. Just the calculus graph of things. And now you take this data here, x1, x2, x3, and so on. And then you just want the sum of these numbers to be n. I guess all the numbers are less than n. So you want this sum to be n, but they're all here. Sorry, this sum to be 2a. And all of the numbers are less than. All of the numbers are less than n. They're actually less than n minus 1 because they are the degrees, right? So because they are the degrees, they're smaller than n minus 1. So what's the minimum of such a sum? According to my notes, the minimum occurs when xi is exactly 2a over n. So minimum occurs when they're equal distance. So if you randomly take n points whose sum is 2a, smaller than n minus 1, if you calculate this output values, the minimum occurs when you take them equal distance. This I don't know how to verify. Probably a calculus result or a little bit more advanced, but the minimum occurs when they're equal distance. That's okay. So what will you get if they're equal distance? 2a over n is the number you will get. So you're summing up I1 to n, 1 over n minus 2a over n. And this should be what we get here. Now this doesn't depend on I, and those numbers are n squared minus 2a. Again, it doesn't depend on n, so you have sum of the same thing n many times, so you get n squared over n squared minus 2a. This tells you that instead of knowing the degrees, if you only know the number of edges on the entire graph, you still can find the lower bound for maximum click size. So you don't need to know as intimate information as degree, but you just have some crude information like edges, number of edges. You can still find an estimate. And again, the number of edges increases will make the lower part smaller, and then this whole thing becomes more. So more edges always means that you'll have a bigger click size. Okay, we will finish. So this is Turans' theorem, which we wrote last time. We'll finish this one, the discussion with cliques and independent sets with the Turans' theorem. I stated this last time. So a graph with m times k minus 1 vertices And k minus 1 choose 2 m square plus 1 edges contains a clique of size k. We discussed how valuable to know if you can find a clique of certain size, right? So any theorem which guarantees that is a valuable theorem, a valuable result. So you want to guarantee that you can always find 10 people are connected pairwise. So when you want to put k equals 10 here, you want to be able to say, okay, I need this many edges to guarantee that. Now this m is there to give you flexibility. So different m's is possible. I could have stated it in different ways as well. But this is a generalization of the triangle result we had, right? When k is 3, we had 2 m vertices and m square 1 edges. So k equals 3 says 2 m vertices and m square 1 edges guarantees that you have a triangle. There exists a triangle. This we proved, and it was a hard proof in your graph in G. And this was hard proof. We had to do induction and a couple of steps. But if you remember with this one, we had an example where this, if you didn't have m squared plus 1, but only had m squared, then you could have a graph with no triangles. And the way you obtain that was to put 2 lines of vertices and only edges from one line to the other one. And because you only have edges from upper line to the lower line, you have no edges between vertices on each line, which means you cannot have any triangles. To have a triangle, you have to have at least 2 vertices on the same line. But we have no edges between them, so you cannot have a triangle. And such a graph has m square edges and 2m vertices. So it's possible to draw it with m squared, but it's not possible to draw it with m squared plus 1. So there's no way to get it with m squared plus 1 with no triangles. Similarly with Turans theorem, with arbitrary k, you can actually draw. So this 2-line business, actually I should say, is just k is 3, so you have k minus 1. So you could actually have k minus 1 places like this. So this is like 1, 2, 3, k minus 1 places. And in each place you could have m vertices. Okay, and each of them we have m vertices. And you could only allow vertices from one group to other one. So these are independent sets basically. That you only have lines there and lines here, but nothing between members in the same clump. Then I will have how many edges? Between these two, I have m squared edges. Between these two, I have m squared edges. But pairwise, how many pairs I have? K minus 1 choose 2 pairs. So I have k minus 1 choose 2 pairs. And on each pair, I have this many edges. This is the total number of edges on this graph. And total number of vertices is m times k minus 1. So as you see, I drew a graph where there's only edges from between these groups and nothing else. Now, such a thing will not have a clique of size k. Again, if you have a clique of size k, because there is k minus 1 clans here and k minus 1 places, at these, by pigeonhole principle, at these two vertices in a sub-size k should be in the same group, because there are k minus 1 places and I have to choose k vertices. So I have to choose two of them in the same group. But if they are in the same group, there's no edge between them. That means they won't be connected. So it can't be a clique. So such a thing has maximum clique size k minus 1. That shows that the theorem is true because of this extra 1. If you didn't have that plus 1, you wouldn't be able to do it. So if you erase that, the theorem doesn't hold. Okay, so let me finish this because I think the clique discussion has been very long. So to finish this, I'm just going to write some inequalities and then we'll get the answer. Okay, so why proof of Turans theorem? So we have n vertices, and that is m k minus 1. And then number of edges. We used the letter a before, so let's use the a again. Number of edges is k minus 1 choose 2, m squared plus 1. So those numbers are. So what's the 2a? Now this number is k minus 1, k minus 2 divided by 2, m squared plus 1, right? So 2a will become k minus 1, k minus 2, m squared plus 2. So you just multiply everything with 2. Let's hit one on somehow. Now, here I have mk minus 1. Here I have k minus 1 and m squared. So you can see that n squared will be lacking k minus 1. So I can write this as this n squared times divided by n k minus 1 times k minus 2 plus 2. I can write this way. Okay, let me not make any mistakes. Now this is definitely bigger than n squared times k minus 2 divided by k minus 1 because it's extra 2. The reason I'm trying to estimate 2a is this previous formula. Okay, this previous formula had estimation at 2a. So I'm going to write now mcg bigger or equal to n squared by n squared minus 2a, and I already have estimation for 2a. If 2a is bigger than this, minus of this is smaller than this, but 1 over will be bigger. So bigger than that one is replaced by this number. Okay, it's minus and 1 over, so it's still bigger. Now n squared cancels, and then you get k minus 1 divided by k minus 1 minus k minus 2. And this is only 1, so you get k minus 1. But it's strictly bigger than k minus 1, which implies that mck, c of the graph, bigger or equal to k. So that means there's a clique of size k. There's always a clique of size k. That's different. I had some questions related to this, but I'm not sure anymore. I have them here. I mean, there are some very standard questions. Let me write one of them. Then there's only 10 minutes left, so we are going to finish with some examples, some questions, and so on. This finishes our discussion about click sizes. So I will do error graphs on Tuesday and the planar graphs on Friday. Okay, so let's do one easy example. Let G be a graph with 33 vertices. Suppose that it's bigger or equal to 27 for all vertices. Show that G has a clique of size 6. I have more questions related to clique sizes. I can't find them now, but this is one of them. One of the exam questions actually in the past. But now this is a straightforward application of the maximum clique size formula, because you want to find that there's a clique of size 6, so all you need to show that there are cliques of bigger sizes. So that means maximum clique size is bigger or equal to 6. That's what you want to show. Okay? The maximum clique size, you have only one way to estimate them. This is that formula. So by formula, you know that this is going to be like this. Now, you have 33 vertices, so that means n is 33. And now you know that each of the di's are bigger or equal to 27. That means minus di is less than minus 27. 1 over means bigger than 1 over 33 minus 27. So you can just continue by saying bigger than equal to. Okay? And that's 6 for you, and you're summing 6 33 times, so you get 33 over 6, which is 5.5. Already it's 5.5 means that any integer bigger than that should be bigger or equal to 6. MC always an integer, so if it's 5.5 means it's bigger or equal to integer 6. But if your click size is bigger than 6, there's always a think about it. If the click size is, say, 8, that means you have a subgraph which has k8. But this means you have 8 vertices where they're all connected, right? So inside it, there's always a k6. Right? Because of that, if your click size is bigger than 6, there's always a click of size 6. And this implies the conclusion that you want. Again, I mean, it's a straightforward inequalities. If you know the inequalities, you're safe. Probably it's almost finished, but let me write one more exam question. As I said, some of these I will send you by email later. For all positive integer k bigger or equal to 2, prove that there exists a connected graph G vertices and E with number of vertices is 2k and the degree for each vertex is 3. It's a prove that question, right? So you think about all the theories that we have done. Which theorem says such a thing exists? And now you end up with actually not finding it, because there is no theorem which says that such a thing exists. And this is a question that you have to actually, I mean, you could have solved this without seeing any theory, basically. You just have to design it. This is called a design type of question. You have to just think about, how can I design a graph with these properties? And how can I set it up? So not every proof that means that you have to write 2 pages. This is actually a question. It will be proved once you draw a picture with 2k vertices with degree 3 on each vertex. That will be proved once you draw the picture. And the proof is very simple. You have n vertices, but because it's, say, k, n is 2k, you have actually 2 groups, k of them and other k prime. And you want degree to be 3. Okay? So the best way to get the degree to 3, first, everything you can put and one edge to their neighbors on a cycle. This is a typical graph where degree is 2 for every vertex. Right? So to make it 3, you just need to make sure that neighbors are not prime numbers. Like the one prime should not be here. If you guarantee that, then you're good. So if you put the k of them here, you want to make sure 1 prime, 2 prime, 3 prime are here, and k prime. Now the degree is 2. You just need to add 1 extra for each of these, and then degree becomes 3. Okay? So once you draw this picture, you get full points in an exam situation. And as you can see, if you didn't take this course, you could have still solved this question. Right? So not everything means you have to use the theory. Sometimes you have to go back and try to remember how you could solve these questions if you didn't know any theory. Okay? So this is all for today. Have a good weekend, and I'll see you on Tuesday.